will be in the opposite direction. Let's now talk about eddy currents. What does eddy current mean? Eddy currents are created when a moving conductor experiences changes in a magnetic field generated by a stationary object, as well as when a stationary conductor encounters a varying magnetic field. For example, if I have an object that is a conductor, well, I'm looking for an object that is a conductor. Suppose this is a conducting material. If this is made to oscillate in a magnetic field, then the magnetic flux linked with the various parts of this conductor will be changing. And that change in magnetic flux will cause current loops to be generated within this object, within this conductor. And you know that the direction of the induced current will be such as to oppose the cause of it. The cause of the induction is the oscillation of this in the magnetic field. And therefore, the direction of the magnetic field will be such that the induced current producing a magnetic field will oppose that. And that means this will produce, the induced EMF will gradually damp the oscillation. And this is what we call eddy currents, the currents that are caused within a conducting object when it is subjected to changing magnetic field. Normally, eddy currents causes heating of a conducting surface. So eddy currents will be generated whenever a conducting object experiences a change in the intensity or direction of a magnetic field at any point within it, and not just at the boundaries. It can be anywhere within the object. For example, something like this. When a metal plate is allowed to fall through a magnetic field, cutting the field at right angles. You can see this is a field at right angles to the board. If you allow a metal plate to fall through it, the flux linked with the conductor changes, inducing an EMF in the metal plate. Now, this induced EMF causes a swirling current. Now, this is the conductor that is falling through. You can see the swirling induced current being generated within that falling object, which generates actually heat. According to Lenz's law, the direction of the induced current is such that the magnetic field produced by it will slow down the rate of fall of the metal plate. The induced EMF is such as to oppose the cause of it. An oscillating metal plate in a magnetic field will be damped due to the formation of eddy currents. In fact, eddy currents is sometimes a menace in many alternating current circuits. So, because of the tendency of eddy currents to oppose the cause of it, eddy currents cause energy to be lost and the amplitude of oscillation of an object in a magnetic field will slow down. Our next concept is what is called self-induction. I want you to understand that concept well. What is self-induction? Now, suppose I turn on a current that flows in this conductor. When I turn on a current, the current in this conductor will first have to increase from 0 to a maximum. Now, during the time the current increases from a 0 to maximum, this conductor is subjected to the changing magnetic flux produced by that increasing current. And that changing magnetic flux will in turn induce a current in the same conductor. That is what is called self-induction. And according to Lenz's law, the direction of the induced current will oppose the growth of current. Is that right? In the same way, if a current is flowing in this conductor, if you turn it off, during the time the current decays from a maximum value to 0, the magnetic flux linked with the conductor also decreases from a maximum to 0. And that will induce a current in the conductor. And that induced current will slow down the decay. And normally, because the decay is faster than the growth, the induced current during decay or during the time when a circuit is turned off is much greater than the induced current during turning off a circuit. That's the reason why I'm sure some of you must have noticed when you turn off a light switch, you often see spark. Spark is created by the induced current. Alright, so consider the circuit where a coil of wire is connected to a battery. When the circuit is closed, the current in the coil increases and the magnetic field generated by the current also increases. That means as the current is turned on, the current in this coil increases. It means the magnetic field associated with that also increases. Since the coil that carries the current itself is subjected to this changing field, an EMF is induced in the coil, which causes a current flow in the opposite direction, because the induced current is always in a direction as to oppose the cause of it. The cause of induction here is the growth of current in here. Therefore, the direction of the induced current will be opposite to that. So when the current is steady, when the current remains steady, no such induction takes place. Self-induction happens only during the time the current grows or the current decays. During the time the current remains steady, no self-induction takes place. Why? Because when the current remains steady, the magnetic flux does not change. It also remains steady. The magnetic flux produced by the current is proportional to the magnitude of the current. Is that right? Greater the current, greater will be the magnitude. That means phi b is proportional to the amount of current, or phi b equal to Li, where L is the constant of proportionality. And this L is called the self-inductance of the coil. The self-inductance of the coil. We represent it by L, and it is measured in a unit called Henry. The self-inductance of a coil is measured in a unit called Henry. 1 Henry is 1 Weber per, 1 Weber divided by, is that right? I equal to, L equal to phi b over I. 1 Weber divided by 1 ampere. And the same as 1 Tesla meter squared per ampere. So the unit of self-inductance is a Henry. We will need to use it in our next lesson. So L equal to phi b divided by I. A coil of wire used in an electric circuit is called an inductor. An inductor. That will be the subject. We'll be talking about that in our next lesson. Now, an inductor with an inductance of 1 Henry produces an EMF of 1 volt when the current through the inductor changes at the rate of 1 ampere per second. You understand that? Now, if I allow a current to change in this conductor at the rate of 1 ampere per second, and if the induced EMF is 1 volt, then the self-inductance of that coil will be 1 Henry. That's what it means. So one more time, an inductor with an inductance of 1 Henry produces an induced EMF of 1 volt when the current in it changes at the rate of 1 ampere per second. Now, since the self-induced EMF opposes the cause of it, the tendency of an inductor is to slow down the increase or decrease of current in a circuit. That means if you continuously turn on and off a circuit, the induced EMF will be opposing that. So we will see that particularly in the next lesson when we talk about alternating current. So the induced EMF opposes the cause of it. So the tendency of an inductor is to slow down the increase or decrease of current in a circuit. It is not like a resistor, but it works almost like a resistor. Now, if there is a fluctuating current in an electrical circuit, an inductor can be used to make the current smooth. You can actually slow down the fluctuation because the induced current will slow down that fluctuation. So if you have a circuit with a fluctuating current, if you want to slow down the fluctuation, the best component to use there is an inductor. Now the symbol of an inductor, again we will see that in our next lesson. This is the symbol of an inductor in an electrical circuit. How about the inductance of a solenoid? Well, we have been talking about solenoid for quite a while now. If I ask you what is the expression for the magnetic field inside a solenoid that carries a current I? Well, I have it right here. The magnetic field inside the solenoid that carries a current I is mu0 Ni, where N is the number of turns per unit length, total number of turns divided by the length. The magnetic flux through a solenoid is, again you know that, phi B is NBA, number of turns, times the magnetic field, times the area. And so that will be, this N can be replaced by NL, number of turns per unit length times the length. So we replace the uppercase N by NL. Of course mu0 times B is mu0 Ni. That's the expression we replaced by this B and A. And that's equal to mu0 N squared ALI. This is the expression for magnetic flux generated by current I in a solenoid. The self-inductance L of a solenoid is L equal to phi B divided by I. And if you divide this quantity by I, you get mu0 N squared AL. And this is the expression that gives you the self-inductance of a solenoid. An example.